Section: Introduction. In this section, we focus on enhancing the reasoning abilities of large language models, LLMs, which is a crucial area of current research. To ensure progress in the right direction, it is essential to accurately assess the current capabilities of LLMs. Typically, the field relies on public benchmarks like GSM-8K, Math, MBPP, Human Eval, and SWE-bench. However, since LLMs are trained on vast amounts of internet data, there is a concern that these benchmarks may unintentionally contain questions similar to the ones used for training. This could lead to models appearing to have better reasoning skills than they actually do, simply by memorizing correct answers encountered during training. To address this issue, we created GSM-1K, a new set of 1250 grade school-level math problems closely resembling GSM-8K. We ensured that GSM-1K had a similar range of difficulty as GSM-8K for a fair comparison. We describe our efforts in detail in the following sections, including how we collected the data. To avoid data contamination, GSM-1K was created solely by human annotators without any input from LLMs or synthetic data sources. We evaluated various open-source and closed-source LLMs on GSM-1K, such as GPT-4, Gemini, Claude, Mistral, Llama, and Phi. Our analysis revealed that many models show signs of being influenced by benchmark data, with the worst-performing model scoring 13% lower on GSM-1K compared to GSM-8K. Furthermore, our findings indicate that certain model families, particularly Mistral and Phi, consistently exhibit overfitting across different versions and sizes. We observed a correlation, Spearman's R² equals 0.32, between a model's likelihood of generating examples from GSM-8K and its performance difference between GSM-8K and GSM-1K, suggesting that models may have memorized examples from GSM-8K, contributing to overfitting. However, all cutting-edge models and all sizes of the Llama 2 family showed minimal signs of overfitting. Despite some models showing overfitting tendencies, all models demonstrated the ability to generalize to new grade school math problems, albeit sometimes at slightly lower rates than indicated by benchmark scores. We have decided not to release GSM-1K publicly at this time to prevent future data contamination issues. Instead, we plan to regularly evaluate major open-source and closed-source releases and update our results continuously. We will make our evaluation code open source for reproducibility. Additionally, we commit to releasing the benchmark publicly when either the top open-source models achieve over 95% accuracy on GSM-1K or by the end of 2025, whichever comes first. Refer to the section for specific release criteria. Our work was inspired by a notable study on overfitting in ImageNet classifiers in 2019. Similarly, we conducted an analysis on GSM-8K, a prominent benchmark for elementary mathematical reasoning. GSM-1K is modeled after the GSM-8K dataset released by OpenAI in 2021, comprising 8.5K grade school math problems. These problems are designed to be solved using basic arithmetic operations and are suitable for grade school students. As of April 2024, top models have reported accuracies exceeding 95%. Other widely used benchmarks for reasoning include Math, MMLU, and GPQA. Data contamination is a well-known concern in the field, and efforts are made to minimize its impact. Methods such as removing data with high n-gram overlap with benchmark data and using embedding similarity have been employed to reduce contamination. Recent approaches like functional evaluations generate unique evaluation data points for each model assessment, reducing the risk of data contamination. Our results, similar to theirs, suggest that LLMs may be excessively tailored to benchmark data. Our method offers an advantage over function-based evaluations by exploring a broader range of the problem space, rather than just variations of the same problem with different numerical values. Section Summary. In this section, we introduce the importance of improving reasoning in large language models, LLMs, and emphasize the significance of proper benchmarking to ensure progress in the right direction. To address concerns of data contamination and existing benchmarks, we present GSM-1K, a new set of grade school math problems designed to mirror GSM-8K, created solely by human annotators. Our analysis reveals evidence of overfitting in some models, with the worst performing 13% worse on GSM-1K compared to GSM-8K, highlighting the need for ongoing evaluations and updates to prevent data contamination issues in the future. Section: GSM-1K. In this section, we created GSM-1K, which contains 1250 math problems that can be solved using basic arithmetic. We used human annotators from Scale AI to generate these problems. The annotators were given 3 sample problems from GSM-8K and asked to come up with new problems of similar difficulty. The detailed instructions given to the annotators can be found in the appendix. All the problems in GSM-1K are designed to be solved using simple math operations like addition, subtraction, multiplication, and division, without the need for advanced math concepts. Similar to GSM-8K, the solutions to all problems in GSM-1K are positive integers. We did not use any language models to create this dataset to avoid any contamination. To maintain the integrity of GSM-1K, we have decided not to release the dataset publicly at this time. However, we are committed to releasing the full dataset under the MIT license when either 3 open-source models achieve 95% accuracy on GSM-1K or by the end of 2025, whichever comes first. At that point, we believe that grade school math may no longer be challenging enough to evaluate model releases effectively. To assess proprietary models, we may need to share the dataset via API. We have taken precautions to prevent data leakage by withholding a small number of validated data points that are not included in the final GSM-1K dataset. These points will also be released when the full dataset is made public. We recommend following a similar approach for future benchmarks, where the data is not released publicly to prevent manipulation but is committed to being released at a later date or upon meeting specific conditions. We will also make our evaluation framework open source, based on a modified version of the LM evaluation harness by Eleuther AI. Despite our efforts to make GSM-8K and GSM-1K similar, they are not identically distributed, and results should be interpreted with this in mind. Quality checks were conducted at multiple stages during the creation of GSM-1K. Each problem went through 3 review layers to ensure correctness, grade school level math, and proper formatting. A total of 2,108 initial problems were reviewed, with 1,419 passing the second review stage and 1,375 passing a general quality audit. To match the difficulty distribution of GSM-8K, we asked annotators to create problems with a specified number of resolution steps, based on examples from GSM-8K. The estimated difficulty was determined by the number of operations needed to solve the problem, identified by counting calculator tags in the solution. However, this estimation is approximate due to inconsistent formatting. We also considered the magnitude of answers, as larger numbers can affect problem difficulty. Problems from GSM-1K were selected to align with the answer magnitude distributions of GSM-8K. We conducted tests to ensure that the difficulty levels of GSM-8K and GSM-1K were comparable. Human crowdworkers were asked to identify the odd problem out of a set of 5, including 1 from GSM-1K and 4 from GSM-8K. The crowdworkers correctly identified the GSM-1K problem 21.83% of the time, which is slightly above chance. Authors who had not seen the data also struggled to differentiate between GSM-8K and GSM-1K, indicating minimal differences in difficulty between the 2 datasets. Section Summary. In this section, we detail the creation process of GSM-1K, a dataset comprising 1250 elementary math problems developed with the help of human annotators. We ensured that all problems were solvable using basic arithmetic and did not involve advanced math concepts, with solutions limited to positive integers. Rigorous quality checks were implemented, including multiple review layers and human differentiation tests, to maintain the benchmark's difficulty level and ensure similarity with the previous GSM-8K dataset. Section: Human Solve Rates. In this section, we examined the solve rates of human participants and language models on the GSM-8K and GSM-1K datasets. To ensure fair comparisons, we had crowdworkers solve problems under time constraints. They solved an average of around 4 problems on both the GSM-8K and GSM-1K datasets, indicating similar difficulty levels between the two datasets. We also checked the solve rates of pre-existing language models like GPT-NEOX-20B and GPT-2 on both datasets. These models showed little difference in performance between GSM-8K and GSM-1K, providing further validation of our findings. To evaluate the models, we used a standardized approach with the same prompt for all models. We assessed the model's performance based on their ability to provide correct answers to questions. Our evaluation process ensured reproducibility and fairness in comparing model performances on the two datasets. Our analysis revealed that some model families consistently performed better on GSM-8K compared to GSM-1K, indicating potential overfitting. On the other hand, frontier models showed no signs of overfitting, suggesting advanced reasoning capabilities or careful data handling during training. Overall, our results shed light on the performance of various language models on different datasets and highlight the importance of considering model generalization and data contamination in benchmark evaluations. Section Summary. In this section, we investigate human solve rates by engaging crowdworkers to solve GSM-8K and GSM-1K problems under time pressure, revealing comparable difficulty levels between the two datasets. Additionally, we assess the solve rates of pre-2021 language models like GPT-NEOX-20B and GPT-2 on both datasets, finding minimal differences. Our evaluation methodology ensures fair comparisons across models, shedding light on potential overfitting tendencies in certain model families while highlighting the robust generalization capabilities of frontier models. Section: Lesson 3. Overfit models are still capable of reasoning. In this section, we learned that overfit models can still reason effectively, contrary to the concern that they only memorize training data answers. Our findings show that even though a model may be overfit, it doesn't mean it lacks reasoning abilities. It just may not perform as well as expected based on benchmarks. Surprisingly, many highly overfit models can still reason and solve new problems successfully. For instance, PHI-3, despite a significant drop in accuracy between different datasets, can solve over 68% of new problems accurately. This performance is comparable to much larger models, like DBRX and Struct. Similarly, Mistral models, known for their overfitting, remain strong in solving problems. This supports our belief that powerful models can learn basic reasoning, even if some benchmark data leaks into their training. Moreover, we explored the idea that data contamination alone may not fully explain overfitting. While it's common to suspect that overfitting is due to leaked test data during model training, our analysis suggests otherwise. By examining how well a model can generate test set examples, we found a positive relationship between this ability and the performance gap between different datasets. This indicates that some overfitting may result from memorizing test data. However, outliers in our analysis, like Mixtral-8x22b and Mixtral-8x22b and Struct, challenge this notion. Additionally, the most overfit model, Math Shepherd Mistral 7BRL, had a low ability to generate test set examples, suggesting other factors at play. Models like Lemma, with known training data containing some test instances, surprisingly show minimal overfitting. This implies that overfitting isn't solely caused by data contamination but may involve other factors, such as how training data is collected or how final models are selected based on benchmark performance. Ultimately, a small amount of data contamination doesn't always lead to overfitting. Section Summary. In this section, we learned that overfit models can still exhibit reasoning capabilities, contrary to the concern that they only memorize training data. The study shows that even highly overfit models can effectively solve novel problems, indicating that overfitting does not necessarily hinder reasoning abilities. While data contamination is considered a potential cause of overfitting, the analysis suggests that it may not fully explain the phenomenon, as some models with high log likelihoods and minimal overfit exist, hinting at other factors contributing to overfitting beyond data leakage. Section: Discussion. In this section, we introduce GSM-1K, a new dataset created to assess LLM overfitting on GSM-8K. When we test various top models, both open source and closed source, we observe significant indications that many models have been influenced by the benchmark data, leading to performance decreases of up to 13% in accuracy. We also notice consistent overfitting in certain model families, particularly Mistral and Phi, across different sizes and versions. Further investigation shows a link between a model's tendency to produce data points in GSM-8K and its performance gap between GSM-8K and GSM-1K, hinting at data contamination as a likely cause. However, we discover that advanced models show minimal overfitting, and even the most affected model families demonstrate strong indications of generalizable mathematical reasoning. We express our gratitude to Dan Hendricks, Adi Ganesh, Akhilesh Praveen, Andrea Jabba, Charlotte Zhuang, Will Zhou, and Celia Chen for their valuable input and recommendations.